if y equals ax to the power of n, then this notation dy dx equals an, so the n multiplied by the a, multiplied by x to the power of n minus 1.
Mm-hmm.
So essentially, if you've got a power, multiply it by the coefficient and then take away 1 from the power.
Mm-hmm.
And just to go through some examples, y equals 4x cubed implies that dy dx equals 12, 3 times 4 being 12, x to the power of 2.
Mm-hmm.
Y equaling 2/3 x to the power of minus a half, same thing, implies that dy dx equals minus 2/6 x to the power of minus 3/2, which applies to minus a third x to the power of minus 3/2, taking away 1 from the power. And then some ones that are fairly quick to get used to, but still worth noting. Y equals, say, 2x implies that dy dx just equals 2. Y equals 5x implies that dy dx just equals 5.
Mm-hmm.
Any constant is just going to multiply by x. When differentiated, will differentiate to that constant.
Okay.
And if y equals just a constant, let's say 2,
Mm-hmm.
that implies that dy dx is going to be equal to 0. And if y equals, 3, that implies that dy dx is going to equal 0. So again, that's just a quick crash reminder starter. Is there anything on this page that is a little bit like intimidating?
So what does dy dx actually mean? So where will I use it?
So this comes from, we may as well go through this then, but this comes from when we're working out gradients between 2 points on a curve. So the idea of dy dx is it's essentially your change in y over the change in x, but your change in x and subsequently your change in y are infinitesimally small. And it's like a really, 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 really good approximation, because the approximation gets better when the 2 points get closer together in which you're trying to work out the gradient between. It being infinitesimally close is what we end up calling dy dx.
Mm-hmm.
So to explain this, I think an example is just best.
Okay.
So if I take, for example, on slide 2, y equals 3x squared. So based on the rule, we already know what the result should be.
Mm-hmm.
Is. But let's just draw a small section of the curve, whatever that might look like. I'm not really trying to get it exact, but it's fine. It's going to look something like this.
Mm-hmm.
And I'm going to pick 2 points on this curve. Let's make it a bit longer, actually. So I've got 1 point here where I call it x for my x coordinate. And then my y coordinate is going to be y, but y is equal to 3x squared. So I'm going to write 3x squared for my y coordinate.
Okay.
Now I'm going to take another point a little bit further along, and it's going to be x plus a little bit more. I'm going to call my a little bit more h. That's my x coordinate.
Mm-hmm.
And then my y coordinate is going to be that substituted into my function, which is going to be 3 lots of x plus h squared, just like that.
Mhm.
And then going back to our work on gradients, we are essentially going to work out the gradient. So the change in y over the change in x. So the gradient is the change in y, so that's 3x plus h. Wait, no. 3 lots of x plus h like that, squared. Take away 3x squared.
Mhm.
That's the change in y, all divided by the change in x, which is x plus h minus x. And we may as well do this from the beginning. To make the approximation better, if this point were to come closer, pardon me, to the other point, then the gradient estimate would be a lot more accurate.
Mhm.
So in the way in which we'd represent that in math terms, without using the geometrical figure, is to say we take the limit as h tends to 0. And let's just think about why that is. Well, it's that if h gets smaller, then 3 lots of x plus, well, let's not even go there. X plus h becomes approximately x.
Mhm.
Like if h were equal to 0, then x plus h would just be x.
Mhm.
So if h is really, 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 really tiny, then it's nearly, nearly, nearly x. Equally, in this part, if the h were really tiny, this would become 3 times approximately x squared, which is the same thing as this.
Okay.
So um, we're just gonna. Well, the thing is, if we were to keep, if I just tidy up what I've done, we see that the denominator just simplifies to h. So 3 lots of x plus h squared minus 3x squared, all divided by h. So now, at this stage, we go, okay, if you wanted to put h equals 0 into this equation, or into this expression, sorry, you'd have a problem because you'd be dividing by 0. So what we need to do is just expand and simplify everything. So the top with our limit as h tends to 0 becomes 3 lots of the x plus h all squared expands to x squared plus 2xh plus h squared, and then that's minus the 3x squared.
Mhm.
And that's all divided by h still. And then we have limit of h tends to 0. And then if we expand out the bracket, we get 3x squared plus 6xh plus 3h squared, all minus 3x squared, and that's divided by h. And then where can we go from here?
So you can cancel out the 3x squared and the minus 3x squared,
Mm-hmm.
giving you 6xh plus 3h squared over h.
Mm-hmm. Nice. And then,
Then you could take out the h in
mm-hmm.
the numerator, giving you, actually, you could take out 3h,
Yeah.
giving you 3h and then in bracket 6x plus h.
Well, actually not 6x, because you take
Sorry,
out,
not 2x. Yeah, 2x.
yeah, so 2x plus h,
Mhm.
all divided by h,
Mhm.
and then
Then the h in the numerator and the h in the denominator cancel out to give you 3 brackets 2x plus h of 1.
Yep, so lim h tends to 0 of 3 2x plus h, because the h's are cancelled, like you said. Then at this stage, we can now just go, okay, let's now pretend h was 0 by actually substituting it in.
Mhm.
And that's just 3 lots of 2x. Notice how I've not put the whole lim thing anymore, because now I've gone, okay, well, now we know what the limit is going to be if h were equal to 0, which we can safely substitute in because we're not dividing by 0, becomes this, which
Okay.
is 6x. That's the final answer. And if you think about the rule for differentiation, that's what we'd do. Like it would become 6x.
Mhm.
So what differentiation is doing is allowing you to work out the gradient, the general gradient function of a function.
Mhm.
And equally, if you did this with like any other polynomial, say like 4x cubed, there'd be a lot more to do with the expanding, but you would get there.
Okay.
Does that answer your question about?
Yeah, it
Yeah.
does. Okay.
And to be fair, this is something that you will learn anyway, like in terms of differentiation from first principles.
Mhm.
So good for you to see an example.
Mhm.
Anyway, this will become a video, and then you can probably watch it a few times, and you can probably apply it to other functions. But that's what differentiation is doing.
Okay.
So you can actually apply differentiation to most other things that depends on rates of change. So anything you've ever thought of that where it's one thing changing with respect to another, for example, speed. You get to a point where you start to model function and model speed, things like moving as functions. And speed is the change in distance with respect to time. So your distance would be like your y, and your time would be like your x. And if you were to call speed s, we wouldn't normally call it in maths s. I don't know why, but you wouldn't.
Mhm.
We'd say ds by dt.
Okay.
T is time. More likely dx by dt, because x is what they would use for like displacement, which is like the vector form of distance. But there we go.
Mhm.
Yeah. So this is what we call differentiation from first principles. And then, of course, we can just extend this to other types of functions too.
Mhm.
So we can apply our rule of differentiation on slide 3 to some more complicated functions or complicated looking functions, which are, well, it's just ones where you have to know your laws of indices, really. So they look a bit daunting, but really they're not that bad. So the ideas of this one are that, well, with the first one, it's just x to the power of a half. The next one is x to the power of minus 1. And the next one, we have to expand the brackets, which becomes 4x squared plus 4x plus 1. And then we can differentiate. And then that becomes a half x to the power of minus a half using our rule,
Mhm.
minus 1x or minus x to the power of minus 2 plus 8x plus 4, going back to the fact that any number times x just differentiates to that number, and then the 1 just differentiates to 0.
Mhm.
And then that simplifies to, yeah, well, doesn't really simplify, but you can leave it like this to be fair, or you can write it in other formats too. So you could probably go a half times 1 over the square root of x,
Mhm.
because the minus a half is 1 over x to the half, and then x to the half is square root, so 1 over the square root of x. Then you have minus 1 over x squared, if you really wanted to write it like this. and then plus 8x plus 4. Does that make sense?
Yep.
Cool. Let's do this. I'm going to leave this here so that you can see this example as we try the next one. I'm going to let you try this one. So if y equals instead the cube root of x plus, let's go 2 over x to the power 3. What would that differentiate to? Or how would you have to rewrite that? Yes, so you've changed it to x to the power of a third. That's the cube root of x. No, okay, I'll just wait for you to think about the other one.
So I want to say it's to the power of minus 2 over 3, but that doesn't seem right.
So what's another way fractionally that you could write 2 over x cubed before you even think about laws of indices?
2 over x to the power of 1/3. No, wait, no, it's not that. No. I'm not sure.
Okay, so over here you've got 2 over x cubed.
Mm-hmm.
This can be expressed as 2 multiplied by 1 over x cubed. Cool. Okay, so 1 over, oh, wait, hold on. Okay, so we've got x to the power of a third. That's cool. Knowing that 2 over x cubed is the same thing as 2 times 1 over x cubed, we then realize, okay, it's 2 times x to the minus 3. Then you have a third x to the minus 3 when you differentiate it, which is, oh, not quite right, actually. So a third, yes.
And
X,
minus
yes.
1 would be minus 2 then.
Yes.
Okay.
So a third minus 1 is minus 2/3.
Okay.
And then this next one is fine because minus 3 times 2 gives you minus 6. And this x to the minus 4. I also noticed that before you rub this thing out, you did 1 over everything. It's not 1 over everything because that power is only being applied to the x, not the third.
Okay.
Yeah, so you've got, yeah. So a third x to the minus 2/3 is the same thing as a third times 1 over x to the power of 2/3.
Okay.
Yes, writing it like that, you realize, oh, okay, that's cool. And if you really wanted to go further, you could say this is 1 over 3 lots of the cube root of x squared minus 6 over the fourth, no, not the fourth root, the fourth power, rather. So 6 over x to the power of 4. How do you feel so far?
I feel okay with it. I think I could do more questions.
Of course. Okay. So suppose you had this y equals 2x plus x plus 1 squared, all divided by x to the power of 7. So it's something like this. We just take it step by step. We first of all just need to expand and simplify. So this is 2x plus the x plus 1 all squared becomes x squared plus 2x plus 1. That's all divided by x to the 7.
Mm-hmm.
Then just going to simplify the top. That becomes x squared plus the 2x plus the 2x gives you 4x. And then that's plus 1. And that's all divided by x to the power of 7.
Mm-hmm.
And now we're just going to take each term and divide through by x to the 7. Or we can think about it like this: x squared over x to the 7 plus 4x over x to the 7 plus 1 over x to the 7. So it's a bit like going backwards with the fractions. You're splitting the fractions up,
Mm-hmm.
or the fraction up into separate fractions, which equals, using our laws of indices, x to the, in fact, let me write it underneath to make it a bit clearer. X to the power of minus 5 plus 4x to the power of minus 6, because this is like an x to the power of 1,
Mm-hmm.
plus x to the power of minus 7, and yeah. And then now we can differentiate it calmly, and we'd say this becomes minus 5x to the power of minus 6 minus 24x to the power of minus 7 minus 7x to the power of minus 8. How do you feel?
I think I got that.
Cool. I'll give you one to try then.
Sure.
The next slide. So if you have y equals, let's be annoying and throw in some negatives as well. So you can do it on paper, you can do it on the Jamboard, however, whichever is easier for you.
Yeah, I'll just set the Jamboard.
Cool.
If I was to make x to the power of minus 3 into 1 over x to the power of 3, would that just switch the numerator and the denominator? Or what would happen in that case?
Say that one more time, sorry. If you were to...
So if I were to make this value or this variable into x to the power of 3,
Mm-hmm.
then what would I do with the 1? Would it just sit there like that, or how would that work?
Oh, yeah. So x to the minus 3 is the same thing as 1 over x cubed. Or you could even treat it the way we did it before, where you're just dividing, but instead of taking away a positive number, you're just taking away a negative number. But yeah,
Okay.
however.
What do I do with that 1?
Well, if you're dividing by 1/,
Mhm.
then the way you would treat like division of fractions would be you'd multiply by the reciprocal. So it's the same thing as multiplying every time there by just a normal
Okay.
x cubed.
Okay.
Mhm. Yeah, that works too. Mhm. 60x to the 4, 6x to the 5. Yeah. So, square. Yep. Yep. Good stuff.
Okay.
Yeah. Okay. Okay. What if we had this? This is, to be honest, just more to do with can you manipulate the expressions. So this one looks annoying. Nice. So you turned it into x to the minus 1, x squared plus 4x. Wait, how come? How did 4x squared become? Wait, how did the 4x? Is that a 4x to the minus 2, or is that just a 2 that you wrote that now looks like a minus 2?
I think that's just, what is that? Okay, so I was supposed to write 2, but I
Yeah.
wrote -2 there just because my handwriting. And
Okay.
then I
Then
mistook that.
actually,
Yeah.
yeah.
Okay. So that needs to be 2, meaning that stays as 4x. Okay.
Yep, x to the 3 over 2, 4x and a half. Differentiate 3 over 2 x to the half. 2x to the minus a half. Yep, that's it. Done.
Okay.
Got it. So yeah, that's basically where you get to, what you get to when you're differentiating um, functions. Like it doesn't anything more than that, and it's just yeah. There's no need
Mhm.
for them to make questions much harder. Like at this stage, you kind of show that you've demonstrated good levels of indices. I mean, even some of the questions I've given have been a bit ridiculous. So yeah, but I did it for the purpose of making sure that you understand your laws of indices and that you know how to manipulate stuff, not because I'm going, oh, if you can't do this, then you shouldn't be doing whatever. So yeah, you done well with that.
Okay.
Let's see. Right, so I'll let you write, but I'll walk you through a little bit what an exam question might be like. So, in fact, this one's just a straight differentiation question. Not even asking you to do any more. So let's go on slide 6. And this is like what the question is. So given that y equals this, find dy dx. And it's 6 marks there. Nice. So 8x cubed minus 4x to the half, yes. Plus 3x plus 2x to the minus 1, yep. Looking good. 24x squared minus 2x to the minus a half plus 3 plus minus 2x to the minus 2. Looking good. Yeah, nice. Okay. Next slide. By the way, well done with that one.
Mhm.
expanded, x squared minus 5x minus 24. Oh, and you simplified it, yeah, to x minus 5 minus 24x minus 1. 1 minus 0 plus 24x minus 2. Yep, that's good.
Would that be the simplest form?
Yeah, that's like that's good.
Okay.
Yeah, that's fine. The next part is asking to find an equation of the tangent. So what we need to do, and it says at the point where x equals 2.
Mm-hmm.
So at this stage, we've got a general gradient function, which is 24x to the minus 2 plus 1. Now to work out the actual gradient at the point where x equals 2, we just substitute in x equals 2 into dy dx.
Okay.
Yeah. Nice.
So that's the gradient of the tangent, meaning that y is equal to
Oh wait, hold on. No, 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 no,
no.
no, 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 no. You made that same mistake again, where you applied the negative power to the 20, like the other thing as well. The negative,
Oh right. So they
yeah,
wouldn't be like. It would just be that.
24 times 1 over 2 squared. Yes.
Okay. Okay. That looks a lot more reasonable.
Yeah, as a gradient. Because the first thing I did was look at that gradient and go, "Whoa, that's like a very yeah."
And we know that x is 2, so
We know
right.
x is 2, yes, but then what's y going to be? So yeah, we've realized that our gradient is 7. Gone y equals mx plus c. We know m is 7 because that's our gradient.
Mhm.
Um, but yeah, we've got an x coordinate, but we need a y coordinate.
I'll do it up here.
Yeah. All right. So let's see. So you've put in 2. Yeah. So yeah, minus 15. Uh, minus 15 equals 14. Yeah, that's it.
Okay.
That's it. That's exactly how you work out the gradient of the equation of the tangent.
Mhm.
Let's see. Oh yeah, I had another question. Which is on slide 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. looking at this question is a bit annoying because it's not really. Well, actually, you could probably write it like you didn't have to start underneath it. You can like write around the page if you wish.
Mhm.
Probably do it in a different color just to make it clear what's the question and what's your writing.
Okay.
So 9 minus 24, yeah, root x plus. Does that say 16x?
Yeah. Yeah,
Cool,
it
okay.
does.
Whatever root x, 9 over root x minus 24 plus 16 over root x, 9x half, plus. Okay, cool. So with this question, when you get a show that question, it's always good to look at what you're trying to show.
Because I need to get ax to the power of a half,
Yeah.
not what I have here.
Yeah. So you've got, how did you get 16x to the minus 3 over 2?
So what I've done is I've made that it's not 1 over x to the power of half. I've made it so that's x to the power of negative half.
Mm-hmm.
And if that's the case, then I need to multiply 16x by x to the power of negative a half.
Mm-hmm.
So when I'm multiplying them, I'd have to do 1 take away a half,
Yeah.
which
Is
not minus 3 over 2.
yes, it's not minus three.
I don't know why I put that.
It's all good. Because when
So
you get show that question, it should almost be like a, oh yes. And now I know that if I'm making a mistake at any stage or not.
mhm.
Hmm.
Then 1 minus a half gives me minus a half, which isn't what they're asking for.
Say that again. 1 minus a half is what?
Is not.
The half.
Yeah, okay.
Yes. And now it's in the form because your A in this case is equal to what's your A equal to?
A is 16 and
And
B
B.
is minus 24.
That's it. You got it.
Okay.
It's all good. Again, this is only the beginning, so
Mhm,
you'll be absolutely fine when you do it with school.
mhm.
Part B, that funny dash notation, is just another way of saying differentiation.
Okay.
So f prime of x, or um, that would be there, the derivative.
I'm just going to put this into my calculator.
Yeah, that's
Yeah.
cool. So first of all, let's check the differentiation. Minus 4.5 x to the minus 3 over 2. Oh. Oh, that's a 16, right? Okay, I missed it. Right. Yes. Square root of. Oh, it all comes up to okay. Minus 2.5. Good.
Minus 2.5 or just 2 point?
Oh,
I
sorry,
got
no,
2.5.
sorry, 2.5. I don't know why I said minus
Oh,
2.5
okay.
because I haven't even worked it out, so I wouldn't even know. But
Okay.
yeah, putting it in the calculator, basically putting in 9 is that's the idea.
Mhm.
So and yeah, the answer is 2.5.